I'll just have to say it again anyway. Okay, so we're going to start off by looking at the first set of transformations that affects the functions, and it's actually the easiest one to look at, and that is what happens to the function when you add or subtract a number. Yes, now there's two types, adding and subtracting inside the function and outside the function. And we call those vertical and horizontal. So say it with me, the entire section, we're going to look at vertical as outside, horizontal as inside the function. Yes? Vertical, outside the function, horizontal is inside the function, whatever we're doing. So now since we're doing addition and subtraction, adding and subtracting, outside the function is going to be vertical, and inside the function is going to be horizontal. Okay? So let's start with a simple one. Let's say your f of x is x squared. Yeah? So the green function is what we call the parent function. That's like the simplest form the function can be in. Yeah? So you only have the one distinguishing factor about that type of function, which is the x squared. Notice we don't have any numbers multiplied, we don't have anything added to it. Yes? So this is called the parent function. Now, let's see what happens. Oops, let's actually change that. It's not the f, let's do a g. So let's see what happens to the function if I add a number. Oops. So it's x squared plus 2. See what happened here. Let me zoom in a little bit. So instead of starting at the point 0, 0, like the original function, the red one started where? At 0, 2. It moved up 2 points, right? 1, 2. That's because I added 2. Now, would you consider this shift, because that's what we call it, it's like you literally grab the function and shift it. Like in size, it doesn't change. Like it's literally the same function. As you can see, it changes it the same way. But it just happened to start 2 points later. Or I should say earlier, I guess. So looking at this here, what do you think? Is this shift vertical or horizontal? Am I moving it to the side or up and down? It went up, right? So that means this is vertical. So the fact that it's vertical means I added outside the function, which is what this looks like right here. So see that? You have your x squared set up right here, and then we added 2 to it. So the addition happened outside the function. I wrote my original function down and then just wrote plus 2. And if you do the subtraction, it will be exactly, oops, what is that? What just happened there? If you do the subtraction, it would look exactly the same. Yeah? So adding and subtracting outside the function is the easiest type of shift. And it is, let's subtract 3, for example. And now we have an orange function. Actually, that's kind of close to the color. Can we change that? Maybe. Let's go to blue. I like blue. All right. So now we have red, green, and blue. So let's look at the blue one. What happened to the blue one? Since I subtracted 3, it moved what? Down 3 spots. And now it starts at the point 0, -3. You see this? So if you add, we're moving up. If you subtract, we're moving down. And all of these have been shifted what? Vertically. They all moved up or down. But it's along the y-axis. Yes, the shift is happening vertically. So, okay. So this is the normal addition and subtraction we know. So what do I mean by inside the function and outside the function? Okay. So let me show you what inside the function looks like. Let's start with, let me turn this one off. Let's start with that one. Oops. So this function right here is actually x squared. So if I want to add to it inside the function, that means I want it to be x plus 2 in here. Oops, I didn't do the plus. Come on. This is annoying. Still writes it as a suffix. Okay. But the idea is that you want to, I don't think I can do it on the website. All right, then let me try and show it to you on paper before we go on. Where's my diagram? Okay, so the idea when you try to shift inside the function instead of outside the function. Okay. Does that look right? There we go. Okay. So, that does not look straight. There we go. Awesome. So first, we did this, right? So vertical shift is when you have f of x set up normally and then you add a number c. Yes, and you can possibly subtract the number c. The vertical shift, because we're doing it outside the function. Now, if I want you to do it inside the function, like the horizontal, then what happens? Then I want you to plug in the addition inside the function or subtraction. Yeah. So what's the difference between this one and that one? If your original function was x squared, for example, so here it would look like this: x squared plus 2, or x squared minus 3, which are the examples that I showed you, right? So I'm adding and subtracting outside the function. Inside the function, it would look like this. So you'd have x plus 2 squared. So it happened inside the defining factor of the function, which is the fact that it was being squared. Make sense? So what you're adding is to x itself before you plug it in. Does that make sense? So I'm adding it inside the squared. Or if you want to subtract the 3, we're subtracting it inside the squared. Let me give you another example. What if the original function f of x was root of x? Now, if we were adding outside the function, so vertical shift, it would look like this: root of x plus 1. If it was a horizontal shift, then it would be root of x plus 1. See that? The plus 1 was under the root. Does it make sense now? So this is outside and this is inside. For one of them, you're plugging it inside f of x. For the other one, you are just adding or subtracting to the function. Make sense? Does anybody have any question about that one? We good? Okay, I'm gonna take that as a yes. So let me go back to my original screen real quick, so I could show you what the function looks like when we do that. Here we go. So since I want to add 2 to this function, and it's not allowing me to do it inside g of x, so I'm going to do it in here. So this is going to be x plus 2, and then here. Yeah. So I'm adding 2 to it on the inside. Let's see what happens. So this is the red line. It's going to move here. And now it's back to being quadratic, and it moved horizontally, but it went to the left, not the right. Please notice that. So with the vertical, we had it move to, had it move up if we're adding and down if we're subtracting, which makes sense. Positive is up, negative is down. But in here, positive is left. And I'm going to explain to you why that happens in a second. Because we're dealing with the values of x. So over here, for example, you have x minus 3 squared. Let's see what happens to the blue function. Let me turn it on. It moved to the right. Yes? So the green one started at the original point 0, 0. Nothing happened there. So when I added 2 to x, it moved where? Left by 2. 1, 2. And now starts at the point negative 2 and 0. And over here, when I added negative 3, I added negative 3 or subtracted 3 from h of x, yes? So x itself, we subtracted 3 from it, and it happened inside the function. It moved to the right. instead of going to the left. Now here's a question I get often. Why is it that when you're adding, it goes to the left, which are the negative values for x, and when you're subtracting, it goes to the right, which are the positive values for x? Why is it backwards, basically? And to explain that, I'm going to switch back to my .com real quick. We're going to keep jumping back and forth. But yeah, okay. So the reason why that happens is because when a function or a value for x is written in this form or that form, the sign usually gets flipped. Like for example, if I give you x minus 3 and tell you to solve that one, yes, x minus 3 equals 0. To solve it, you're going to grab the negative 3, move it to the opposite side, and x equals what? Positive 3. Yeah, that means if you want to move to the positives and you want this value to be written in a parenthesis form, then it's going to be x minus that value. Whenever you see this, you know that that x value is actually positive. Here is going to be negative because it was positive before you solve for it. The 2, you move it to this side and it turns negative. Now x equals negative 2. That is why when we plot x minus 2, this is going to move to the right, but x plus 2 is going to move where? To the left. Because when it's minus, it's going to turn positive. But when it's positive initially, when you solve it, it's going to turn negative. Does that make sense? So with the horizontal, everything is going to be practically backwards. Look at it that way. The vertical is going to do what you expect it to do. The horizontal is going to do the opposite of what you think you should do. Make sense? So is everybody with me so far? You're too quiet. Yeah? Okay, good. So let me go back to the graph real quick because I want to make sure you got that part. Okay. You all see what I'm looking at? Doesn't look like it. Are you seeing it? I don't think you're seeing it. No, yeah, I figured. It's not showing it to you for some reason. Let's stop. And then start again. Maybe I'll do it this time. Is that the first time it did that? Like, were you seeing what I was pointing at before? Okay, let's try again. Okay, so I think you're seeing it now. Okay, there you go. Awesome. So again, with the horizontal, subtraction goes right, addition goes left. With the vertical, addition goes up, subtraction goes down. Now, think about it. Positive goes up, negative goes down with the vertical. The horizontal is going to do the opposite of what you think it should do. So the negative is going to go right and the positive is going to go left. So far, so good? So that's what we're talking about as far as shifts are concerned. Yes, we're adding and subtracting numbers horizontally and vertically. And remember, with all the transformations I'm going to show you, vertical happens outside, horizontal happens inside the function. Okay, so before I move on, if you have your notes, I want you to draw 2 tables, and we are gonna graph both of them, 2 functions. So I need to switch back. This is gonna get irritating fast, but I guess it's the only way to do this. Okay, so where's my document? So if you have the notes, you just need to flip the second page. If you don't, you can redraw this. It's not that difficult. So I just need you to do a 3-column table, actually 4-column table. First one is the x value, yes. The second one is the parent function, which is y equals root of x, square root of x. And the other two are the two functions I want you to try and graph and see how the shifts happen. For the first one, we're adding a number and it's outside, so it's root of 2 plus 2. And for the second one, it's root of 2 of x plus 2. I was saying 2 for some reason. Root of x plus 2 and root of x plus 2, but the whole thing under the root this time. Yes? So G and F, each in their own column. And we're going to start to plug in. So when you guys are ready. Does everybody have their tables? So you have two functions you need to write down. All good? Is anyone not ready? I should ask that. Is anyone not ready? Okay, take that as a no. Here we go. So for the first one, you already have the values filled in. If you don't, please write down the numbers 1, 2, 3, and 4, and 0. I forgot to mention 0. So 0, 1, 2, 3, 4. Each in their own line, because these are the x values we're going to plug in. Okay? From 0 to 4. And then we start. The first one is the parent function, which is just square root of x. So what I'm going to do is plug in these values into that function to find what the y value would be. Yeah? So 0 under the square root, so square root of 0 is still 0. Then square root of 1 would still be 1. So the answer is still 1. Now square root of 2 is square root of 2. There's no solving that one. Square root of 3 is square root of 3. There's no solving that one either. Okay. Square root of 4 equals what? 2. Right? So these are my values. 0, 1, root of 2, root of 3, and 2. Okay. Now let's look at that one. Well, we said that the g function, where you have the 2 added on the outside, this is going to be a vertical shift because the addition happens outside the function. Yes? And since we're adding 2 to whatever this value is, that means you grab these and you just add 2 to that number. Okay? So here we have 0 plus 2 is 2. 1 plus 2 is 3. Root of 2 plus 2 would be root of 2 plus 2. Root of 3 plus 2. And then 2 plus 2, which is 4. Yeah? Okay, what about that one? Well, here the addition happened inside the function. That means we're adding the number to the x value, these values. Yes? So that's what we're going to plug in. So x is 0. 0 plus 2. 0 plus 2 under the root, which means this is the root of 2. Yeah? X is 1. That means you're going to add 1 and 2, which gives you 3. So this is root of 3. Over here, we have 2 for x. 2 plus 2 is 4. So this is root of 4, which equals 2. Yeah? Over here, we have what? 3 plus 2, which is going to be 5. 3 plus 2. So that is the square root of 5. And over here, we have 4 plus 2, which is the root of 6. Yes? Okay, now here's something I want you guys to notice. We have, for the x values, because we did the horizontal shift, yes, when you added numbers to the x values, you basically function just 2 steps to the left. That means that the first point started at this value. See that? So the y value, which is the root of 2, for the x equals 0, actually starts at x equals 2 for the parent function. You see this? So for the original function, it was 2 root of 2. For this one, it's 0 root of 2. So we shifted by 2 points. Notice that? And it's to the left. Anyway, so we're going to graph these. Ready? Okay. So I'm going to try and graph my parent function to both, and then do each one of these on their own square. Okay, let me see. So the parent function we have the 0, 0. So we're going to start with that one. And then we have 1 and 1, which is right here. And then we have the point 2 and the root of 2. Now root of 2 is like, so 2 for x, root of 2 is a little more than 1. I think it's like 1, almost a third, but not quite there. And then 3 and root of 3. So 3 is right here. Root of 3 is just below 2, but not quite, so right there. And 4 and 2. So it's 4, the point is 2. And that gives you the pattern. And square root of x function looks like this. That's our function. Now I'm going to mirror that over here. So we said this is point 0, 0, 1 and 1, 2 and 1/3, 3 and 1/7-ish, and then 4 and 2. Like that. And do the same. Okay? So that's my original function. Yes? I'm going to do this one in blue. The addition outside the function. So we're going to shift it vertically. Okay. So let's see. We have the point 0 and 2 first. So 0, 2. So this is where it starts. So it moved up by 2. And then we have 1 and 3. So 1 and 3. Okay. And then we have 2 and root of 2 plus 2. So we said root of 2 is like 1.34-ish. Right? So plus 2, that would be 3.4-ish. So at x equals 2, this is going to be above 3 by a little. Look right here. Okay. Now 3, root of 3 plus 2, which is the same. So it should be right around here at 3.7-ish for 3. And then we have 4 and 4. And 1, 2, 3, 4. There we go. And 4. Just right here. And it looks like that. So the functions should be identical, just what? Moved up by 2 points for the y. All right. Now let's do the other one. I'm going to use red this time. So I'm going to do the horizontal shift, the red pen, which is this function. Okay. So again, we'll look at the x values and the y values. We have 0 and root of 2. So x is 0. Y is what? Root of 2, which would be like 1.3, which is right here. Okay. Now we have 1 and root of 3. This is 1. This one is going to be 1.7, which is like right here for y. You see the points? And then we have 2 and 2. So x is 2, y is 2. Okay. And then we have 3, right? So we have 3 and root of 5. So add 3 Root of 5 is like 2.2. So x is 1, 2, 3, and this is going to be 2.2, which is right here. And then at 4, it's root of 6. No, root of 6 is like 2.4, 5, 1, 2, 3, 4. So right here, and then about the halfway point between 1 and 2 for the y. Yeah. There. See that? That red line? Okay. That means the function looks like this. Now here's a question I've gotten before. That looks like it went up. It's like, no, it didn't. It's just that the points you graphed started at this point. Now keep in mind, we said that +2 means it's going to go to the left points. Now, when we started graphing this point, it was the equivalent. Remember when I said 0 and the root of 2 is the equivalent of 2 and the root of 2. Do you remember that? That means we're already 2 points ahead. As far as this function is concerned, we didn't graph the first 2 points. The other one did. So if you want to backtrack, then the point 1 and -1 and 0 at -2, the function looks like this. Make sense? Do you see why I pointed that out? Now on the test, if I'm going to give you something similar to this, I'll probably ask you to tell me what the transformations were and graph it once that's done. But when I do that, it will be more than one at once. So far, we're going to look at them one transformation at a time until you get what they are. So these were the shifts. Before I move on, I want you to do these with me, but I'm going to graph it on the GeoGebra graph instead because it's going to look neater. Yes, but here's the question. So we have the z of x equals x plus 1 squared and then -4. Yes? So as you can notice, I'm doing both transformations at the same time. We have the inside and the outside. We have x plus 1 squared -4. So before I graph it, can you guys tell me how many spaces are we going to move horizontally and how many spaces are we going to move vertically? And are they negative or positive? Like, is it up or down, left or right? What do you think? So horizontal shift, which is on the inside. Where are we moving, left or right? For the horizontal one. We're moving 1 left, 4 up, left, 1 space to the left. You're right, yes. So this is going to be moving to the left by 1. And this one, vertical, is going to up or down. Well, we have a negative. And remember, the vertical behaves exactly the way you expect it to. It's the horizontal that doesn't. Yes? So a negative means down. So this is going to move down by 4. But let's see it. Okay. Now, what would be my parent function for this one? Can you tell me? Like, what's the defining characteristic? I can't speak this morning. What's the defining characteristic about this one? It's x squared, because you see the x and you see that it's being squared. Yeah? Okay. So let's look here. Okay. Here we go. Are you seeing it? Yes, you are. Awesome. So I'm going to turn this off real quick and use that one. And -4. And I want to make this a 1. There. Okay, so we're adding 1 and subtracting 4. Let's see what happens to the red one. Red function. So this is what happens when you do both together. So the point 0, 0, as far as the y-axis is concerned, it moved down by 4. So we went all the way to -4 for the y. See that? That's -4. but it's over here because we also moved it one space to the left. Make sense? So you moved it to the left horizontally by 1 and down by 4. So it's right here. It's both together. Okay? Now let's do the next example in the notes. Number 4. That one says the absolute value of x minus 2, all that is inside, absolute value of x minus 2, and then plus 3 on the outside. So I'm gonna graph your parent function, which should be the absolute value. Like that. That's my absolute value function. It looks like a V, which is actually pretty cool. Because remember, absolute value functions don't have negatives or positives as far as the x is concerned. And that's why it looks like a V, because that means that whatever value for x, whether it's negative or positive, the y value is going to be exactly the same. So it's like aligned, and it never goes to the negative. That's why both lines are up there. And it looks like a V. X minus 2 on the inside, and then we're adding 3 on the outside. So this is what I want to graph, right? So do you think that the minus 2 on the inside is going to move it left or right? How are we moving? Left or right? Let's look at it here. How did it go? We went right since I'm subtracting 2. Okay, now adding 3, we're going to take it up or down. Took it up vertically. So along the y-axis, we went up by 3, and we went to the right by 2. So the starting point now is right here. Yeah? Any questions about these two? So that was shifting, both vertical and horizontal. Now I'm going to show you shrinking and stretching for the vertical and the horizontal. Now keep in mind, again, vertical happens outside, horizontal happens inside, no matter what the operation is. Okay, now before I start showing you the graph, I actually want to show you a little table to help explain what happens when we multiply. Okay, so multiplication, I'm going to remove the notes for a sec. Multiplication is what we are going to do when we are dealing with shrinking and stretching, both of them. We're going to be multiplying. So let me show you the difference here. Okay, so the numbers we're going to multiply by are all going to be positive, yes? You're never going to multiply by a negative number. We are reserving the negative for its own transformation. So multiplying by two types of numbers. The first, let's call it A, that's the number you're multiplying by. The first is going to be bigger than 1. Okay, so a number that's bigger than 1, that's going to be your first multiplication type. The second one is when A is between 1 and 0. Okay, that means it's like a teeny tiny number. It's still not negative because it's bigger than 0, but it's less than 1. And I'm talking like 3 over 8 or 1 over 2, you know, fractions. Something tiny. Okay, so these are my two types. Now the same type of multiplication is going to happen to the function both vertically and horizontally. So I'm going to draw a line and show you what happens to both. Okay? Here's my weird table. I can't draw a straight line to save my life. It's ridiculous. Okay. So when we're doing something vertically, then this multiplication is going to happen what? Outside or inside the function? What do we think? Outside or inside? Vertical. It's outside. Yeah. So the A I'm going to multiply the function with is going to be right outside. Like that. Right outside. Like that. For both. Now, what happens when you multiply by a number that's bigger than 1? Then vertical function is going to stretch. And by stretch, I mean you're literally going to grab whatever graph you see and pull vertically. It's going to stretch. Think of a rubber band that's getting taut. Yeah? Now, what's going to happen when you multiply by a number smaller than 1 but not by 0? It's going to shrink. So again, with the vertical, the function is going to behave exactly the same way you predict it to. So when you multiply by a number bigger than 1, the function is going to get bigger. It's going to stretch. And when you multiply by a number smaller than 1, the function is going to get smaller. It's going to shrink. Make sense? So stretch, shrink. Vertical always behaves the same way you think it will. Horizontal is always going to be the opposite. So over here, if I'm multiplying horizontally, that means what? I need it to be inside the function. So what does a multiplication inside the function look like? Looks like this. F of ax. Because we're multiplying the x value, not the y value now. So, because again, remember, the result of the function is always your y value. So vertically, you're multiplying the y value. Horizontally, we're multiplying the x value. See that? So it's going to be f of ax for both. Whether the number is big or small, that's where it goes. Make sense? Okay. Now multiply by a number bigger than 1. What's going to happen here? It's going to shrink. Smaller than 1 is going to stretch. Like I said, vertical behaves the way you want it to, horizontal, the opposite. Okay? Now, since I said that for vertical, you are basically multiplying the y value, let me give you this. So for the vertical column, and this applies to both these two, but I just want to write it here. For the vertical value, the original coordinate you start with is xy, yes? After the multiplication, it becomes x and a times y, whatever a is. Make sense? So it's the same x value, just the y value got multiplied. You with me? Okay. So what about the horizontal? So, okay. xy. Now where do you think the multiplication is going to happen? To the x, correct? We're going to multiply it by the x instead of the y value this time. Only please notice this part. For the x, it's actually going to be x times 1 over a. The opposite. Over here, just a number. Over here is 1 over a. And that's why when you multiply by a big number, it shrinks. But when you multiply by a big number, a fraction of a fraction is a whole number. So it's going to stretch. Are we seeing that? So 1 over a. Or if you want, you can just write it as x over a. That makes it better. Okay, so please write that down. This applies to both the numbers. Sorry, you're not saying it. To both. If the if the number you multiply by is bigger than 1 and 0. This is what happens. Now I'm going to explain why over this. But let's start with the vertical. Let's look at the graph. Actually, was honestly one of the ones I was more worried about because flipping back and doing it virtually would not be as clear, but I think it's okay so far. Ooh. I think my connection is starting to cut off. Do you guys hear me? Yeah? I don't know. It says that I have a bad connection, but I don't know if you're still there. And it won't share tab. You're cutting off. Are you seeing the screen? I don't think you are. Oh, there we go. All right. So, okay, keep me updated if you see what I'm doing or not, because I'm looking at the page and the collaborate. So if you think I'm on and off or anything, just let me know. If I hear a chat pop, I'll look at what you guys are saying. Okay, so let's look at a function. Let's stick with absolute value for now. Okay, we're gonna look at stretching and shrinking now. Okay. So for this, we're gonna multiply by a number. Yes. So my parent function is the green one, which is I don't know. It's behaving all. That's not good. Okay, how about now? Better now? I think resetting helped. Okay. So, okay, awesome. So, the green function is my parent function. Yes, this is the original absolute value function. Now, the red function is going to be a vertical shift. I'm going to remove everything else. I'm going to multiply by, let's say, 3, just for fun. Okay, so here's what it looks like. And notice, when we're dealing with vertical and horizontal shifting or shrinking, the function isn't going to move from where it originally was. This is not a shift, yes? So we're not going to move left or right or up and down. We're just going to, oh, it did. It shows that I have a kind of good connection. I don't know, let me reset and see if that helps. Is it better now? I think that helped. I don't know. 1/3. You guys there? Yeah? Okay, good. All right, so let's look at them one by one. I'm going to turn off the blue function a little bit. Still frozen. I'll leave in Zoom. Oh, okay. All right. So, is it he the only one? Okay, no, he's not. Okay, tell you what, I'll stop sharing and redo it, hoping that that would fix it. Okay. Let's try. Okay. Here we go. Okay, is that better? I think it's supposed to be working now, hopefully. Okay, so I'm looking at a vertical stretching right now because what? Because I'm multiplying by 3, yes? So the red function is going to be a stretch and the blue function is going to shrink, but I have the blue one turned off, so let's look at the red one only. So green is my parent function. Do you notice how the red one is thinner than the green one? Like it grows higher faster, because that's what's really happening. So it's kind of like you grab the absolute value function and you pull at it. Remember the rubber band example? Or I just call it a metaphor. So over here, for the absolute value function, I'm going to zoom in a little bit. Okay. For the absolute value function, as you can see, at the point 2 for x, for example, y was 2. But for the red one, at x equals 2, y is all the way at 6, because I multiplied it by 3. You see that? So the point 2 for x, instead of being at 2 for y, is already at 6. So it climbed a lot faster. Make sense? So this is a vertical stretch. You pulled it along the y-axis. You see that? So it's being taught vertically. Okay? Now a vertical shrink, which is the blue one, is the opposite. It's growing slower. Make sense? So it's like it was squeezed, it shrunk. The rate reduced a lot. So for the point 2 for x, instead of just like the green function being at 2 for y, the blue one is at what? 1/3. No, 2/3 actually. It's right here. 0.2/3 for y. So it's 2 and 2/3. And for 1, it's at 1/3 for x. Sorry, for y. 1/3 for y. And why is that happening? It's because I'm multiplying it by 1/3. So after you get the x value, which is 1, multiplied by 1/3, the point is right here. 2 times 1/3 is 2/3, which is right here. Now 3 and 1/3, it takes you all the way to 1, which is right there. See that? So x had to climb all the way to x equals 3 before y was 1 for the blue function. Well, for the for the green one, at x equals 1, y was already 1. See that? So it climbed at a far slower rate, a third of it to be exact, because we're multiplying by 3. So far so good? So vertical stretching and shrinking is kind of simple. You just multiply by a number and you expect the exact result that you see. If you multiply by 3, it's going to grow faster and higher 3 times. And if you multiply by 1/3, it's going to grow at a slower rate, a third of the original rate to be specific. Okay? So like I said, vertical always does what you expect it to. Horizontal is going to do the opposite. Okay, that was the vertical one. Now let's look at the horizontal. Okay, so for the horizontal, we said that we multiply on the inside, yes? So now the 3 is going to go inside the function. So it's going to be inside the absolute value bars, not outside. Oops. Okay, so that's 3x. And let's do, oops. Can I add it to it, or do I have to rewrite everything? Probably not. Okay. Shot. I deleted everything. Awesome. This is not going well. Okay, there you go. So I'm gonna turn on the red and turn off the green. Okay. Now, who thinks this looks exactly the same as before? Multiplying the 3 by on the inside the outside. Does it look the same to you? Absolute value, the green one is still bigger than the red one, right? This looks like it's being vertically stretched, correct? Well, see, the difference is now we're looking along the x-axis, right? Not the y-axis. So I want you to look in comparison with the x values, not the y values this time. Yes, so we're gonna grab steady y values and compare the x values for them. Make sense? So for the green one, when y was 1, x was 1. Yeah? So y is 1, x is 1. But for the red one, when y is 1, x is what? 1/4, or no, 1/3. You see that? It's 1/3. So x got what? The x value got shrunk. Does that make sense? So when the function grows faster for y, it's actually growing slower for x, because that means the x values are going to be a lot smaller by the time y climbs really high. Make sense? So at y1 for the red one, x is 1/3. It got divided by 3 instead of multiplied by 3. And that kind of explains to you the point reference I just made, where I said the point, instead of being xy, it becomes x over a, comma y. Make sense? So when you multiply by 3, the horizontal function is going to shrink, because horizontally it did. The green function is the parent function, and as far as the x-axis is concerned, the red one is smaller than the green one. Does that make sense? Along the x-axis, red is smaller. So now let's look at the blue. Now that's bigger as far as x is concerned. x got bigger. Now, when y is 1, instead of x being 1, x is what? Where is x 1? At 3. You see that? So y1, x is all the way at 3, right here. And that's why, even though you see the exact same function, how we look at it is the difference. So when you're doing vertical stretching or shrinking, you're looking at the y-axis. When you're doing vertical, you're looking at the x-axis. Does that make sense? So here, the point, since we multiplied x by 1/3, the point is going to be x over 1/3, which means it's x to multiply by 3, which is 3, since x is 1. Yeah, so at the point x is 3, y is 1. But for the green one, when y is 1, x is 1. So x got bigger. So multiplying by a number bigger than 1, like the red one here, the function is going to shrink horizontally. When you multiply by a number that is between 0 and 1, the horizontal function is going to stretch. Make sense? So like I said, every time horizontal does what you expect it to, vertical does what you expect it to, horizontal is going to do the exact opposite. Okay? Did everybody get that one? If not, please ask. Don't worry about it. Yeah? Any questions at all? Okay. If not, I actually have a fun example for you. And it's about the horizontals. But let me share my document for that one, because it's in your notes. If you have the notes printed, it's question number 7. Right here. This one. I've never brought this on a test before, but I think it's fun to do in class. And who knows, maybe I'll give it to you. So here's what I want you to do. The function is f of x, and I gave you the graph. Yes? And I want you to graph y equals f of 4x. That means multiplying it by 4 inside the function, yes? So this is going to be a horizontal what? Shrink or stretch. It's not going to grow bigger, it's going to grow smaller as far as x is concerned. So this is a horizontal shrink, yes? So I want you to graph this one. Now here's the problem. I didn't give you an equation for the function. You don't know what that is. You just have the graph. Yes? So usually you have the equation, you draw a table, you plot the points, and then you connect the dots, right? Well, now I don't have an equation. So how are you supposed to graph this one here, but multiply by 4? Well, let's think about it. The points this function has are what? We have -3 for x, -1 for y. And then we have -1 for y, +1 for y. So it's like this. And then we have +4 for x and -3 for y. And last but not least, 6 for x and 3 for y. Sorry. So it's +x, 6 for x, and 3 for y. Okay, so these are our points. All right, now let's think about it. Do you remember the point reference I made in the table before we looked at shrinking or stretching? So these are the points for f of x. Now I want you to give me the points for f of 4x. Yes? But how are we supposed to figure them out? Now, I can easily pick x values because you always just choose those normally. And we need to figure out the y value. But with the division, that's impossible. So instead, like I said, when you're dealing with the horizontal stretching or shrinking and you want to compare both options, what you do is make the y steady and you see it gets affected. Okay? Okay. So to do that, when this function had y to be -1, x was negative. So what about this one? If y is -1 here, what would x be? And remember, I said that the shift between the two happens like this. You have x to y, and then it becomes what? X over 4 and y. Yes? Why? Because I'm multiplying by 4. So knowing this, y is still going to be the same. So when y was -1, x was -3 for this one. When y was -1, x is going to be what? -3 over 4 for that one. Are you guys following me? So here we have what? 1 for y. X was -1, now it's going to be -1 over 4. What about this one? So x is -3. Sorry, y is -3. X is going to be 4 over 4. Yeah, which is just 1. Okay, what about this one? Y is still 3. X is going to be 6 over 4, which simplifies to 3 over 2. See what I did there? Now that I have my points, let's plot them. So we have -3 over 4, which is like -3/4. So right here for x, and -1 for y, so it's right about here. Okay. Then we have -1/4 and +1. -1/4, and then you go to +1. Graph it right there. Okay. 1 and -3. So 1 and go all the way to -3. And then you have 3 over 2, which is 1.5, and +3. That's 1, this is 1.5, and you go all the way to +3, which is right here. And then you connect the dots. And that's your function multiplied by 4. It horizontally shrunk. It looks more taut, but what happened really is that it shrunk horizontally. You see that? Did everybody get this one? Any questions? No? Okay. So that was horizontal and vertical, stretching and shrinking. One last transformation, I swear, and then we're done. Okay? One last type. This one is called reflection. This is where we use our negative. Yes, because so far, all I did was multiply and add, and the multiplication, I didn't allow you to multiply by a negative, right? I just said the number has to be either bigger than 1 or between 1 and 0. A student once, though, they asked me, why are we not multiplying by 1? Because if you multiply by 1, you end up with the parent function itself. You didn't read anything. Does that make sense? And if you multiply by 0, then everything disappears. That's why. So those are not included because they're not relevant. Yes? So this is the example we're going to do together. But I was looking for the page. Oh, there we go. It's actually at the bottom of the one we were on just now. Okay. Now on your notes, if you notice the entire note set, it explains everything I told you so far. So this is the section that talks about reflection. So in the reflection, you have two types. One that's going to happen across the x-axis, and the other is going to happen across the y-axis. Yes? Now, here's the thing. The one that happens across the x-axis is going to be your vertical. And the one that happens across the y-axis is your horizontal. Wait, why isn't x horizontal and y vertical? It's because what's happening across it, that means the direction is going to be horizontal, and here the direction is going to be the vertical. Now let me explain why. When we talk about reflection, usually you are mirroring a function. That's the idea. Yes? So if the function you have is mirrored along the y-axis, yes, and by that I mean like this, in that direction or that direction, okay, so along the y-axis, then it's happening across which one? The x-axis. So when the reflection is happening vertically, it's going to happen across the x-axis. And when the reflection is happening horizontally, in this manner, is going to happen across the y-axis. You see that? That's why vertical reflection happens across the x-axis, horizontal reflection happens across the y-axis. Now, here's another tell that should help you understand that one. Here, as you can see in the definition of what it is, reflection across the x-axis, look at the function. Y equals negative f of x. The negative is where? Outside the function. Remember, vertical is always outside, horizontal is always inside. Yes? So negative f of x is a vertical reflection. And f of negative x, see that? The negative got in. So f of negative x is a horizontal reflection. Okay? Now this one's the easiest one. So let's have fun with it. Here's the question we're going to do together. Number 8. Okay, this is the original function. This is what I want you to reflect. Now, when we're reflecting, we're going to be mirroring the points. Now, here's the purpose of it. When you're doing a vertical reflection, negative on the outside, the point, which was xy here, for this one, the original, here is going to be what? What's turning negative? The y value, yes? So that's going to be a negative y. Yeah? For that one, the x value is the one that's turning negative. So here is going to be negative x and positive y, or whatever y is. But you're going to flip the sign for x. Okay? So the point values you're going to use are going to be exactly the same, which is going to flip the sign. Okay, so here's what I'm going to do. I'm going to redraw this one to both, and then graph each one of these in a different color, so we can compare on the same graph instead of looking back here every time. So let's see, 0, 0. We have the point 1 and 1, so it's right here. And then we have, where's that, 3 and 3. Yeah. And then we have 1 and 4, like this. Okay. That's my function. Same. Repeat the process. And then 3 and 3, right here. Okay. Okay. Now, I'll do the first one in blue. So this is the vertical one, because the negative is on the outside. So let's start. So since it's vertical, is this going to happen across the y-axis or the x? What do you think? X or y? It is the x-axis. This one, since it's, oops, let's use the different color for that one. For that one, when it's horizontal, is it going to happen across the x or y axis? This one is the y axis. Okay, now let's focus on the vertical first. So, okay, so now we're doing vertically. Every y value is going to turn negative. Okay, so the point 0, 0 stays where it is, because there's no negative 0. All right, now when x is 1, y was positive 1, now it's going to turn to a negative 1. So it gets mirrored right here. Okay, now when x is 3, y was positive 3, is going to go all the way to negative 3 now. So it goes there. And then when x is 4, y was 1, and it's going to turn to -1. That's my new graph. So let's connect the dots in the same manner. And this is my function. See that? They look exactly the same, or they're supposed to look exactly the same. And the reflection is happening across its axis. As you can see, it's the x-axis. Yeah. But this is obviously vertical, right? It flipped vertically. The direction is vertical. Okay, let's do the horizontal one now. Let me switch color. Okay, so now the x values are going to turn negative. Yes? So 0, 0 stays as 0, 0. Now, when y is 1, x was positive 1. Now it's going to become negative 1. So right here. Okay, when y was 3, x was positive 3. Now it's going to turn to negative 3. So right here. And then when y was also 1 again, x was positive 4. Now it's going to become, oops, negative 4. So right here. So the function looks like, oops, like that. Now the reflection happened horizontally, which means it's across the y-axis. Yes? Any questions about the fraction? Anything at all? Okay. Now here's the best part of the notes. This table right here. This table has every single thing I said so far. I'm trying to make studying easier on you, because I know this can be a little confusing. So here you have the transformation, how it affects the graph of the function, and how it looks on the points. Everything. Vertical translation, or shift, you call it shift. You're adding, subtracting a number outside the function. Yes? And the function is going to go up or down. So if it's plus, it's up. If it's subtraction, it's down. And to the point, you're basically just adding and subtracting to the value of y. The horizontal shift, same thing, but inside the function. And when you're subtracting, notice I wrote that first. When you're subtracting, it goes right. When you're adding, it goes left. And here's what happens to the point. Notice, if you're adding, x is minus h and the point. Saw that? Because when you solve for it, it turns positive or negative. That's why. So like this, you add, like that, you subtract. It's the opposite. Please notice that. Okay? Now, vertical, stretch and shrink, multiplication happens outside the function. If you multiply by bigger than 1, it's a stretch. Between 0 and 1, it's a shrink. So the graph gets shrunk or stretched vertically by a factor of a. And the point is where you multiply y by a. For the horizontal one, the multiplication happens inside the function. Again, it's a shrink if it's bigger than 1. It's a stretch if it's between 0 and 1. And the factor of stretching or shrinking horizontally is what? 1 over a. Down. And the point, see that? X over a and y. Lastly, reflections, which is what we just looked at. Across x and y-axis. All right? Now here's the part we didn't mention so far, because everything I showed you was one type of transformation at a time. Yeah? We either did shifting, we did stretching, shrinking, and then we did reflection. I didn't mix them up, but there is an order. If I give you a question that has more than one of these, then there's a specific order to follow when you're executing them. Otherwise, you end up with the wrong result. Here it is, written down here. The first transformation you need to do is the horizontal shift. Yes? Horizontal shift being this one, not the vertical, horizontal, that one. The adding and subtracting inside the function. That's the first one you do. The second thing you need to do is stretching and shrinking, horizontal or vertical, doesn't matter. You do those first. Yes? So horizontal and vertical, stretching and shrinking. So any multiplication you have, that's the second thing you deal with. And if you have more than one type, doesn't matter the order, you deal with them after the horizontal shift and before anything else. Okay? So first, horizontal shift. Second, multiplication, whether inside or outside the function, no matter about what number. Third is reflection, that one. You deal with the negatives. You flip the function in the order you need to after you finish those two. And the last thing is adding and subtracting to the function on the outside, which is the vertical shift. Okay? So that's the order you need to use every time you solve any problem. Now, we'll use that. Here we go. Example number 9, 10. 9 is already solved. So this is just to observe what happens to the function. Yes? So I gave you f of x equals 2 times the absolute value of x plus 1 minus 3. And I said that f of x is the absolute value of x. This is your parent function, the red one right here. Okay. This is the graph of the final result after we did all of these. But let's identify the transformations. Looking at this right here, we have what? How many? We have 3. Yes? We have a multiplication, we have an addition on the inside, and we have subtraction on the outside. The first thing you need to deal with is the horizontal shifting. So addition or subtraction on the inside. Here we have addition. Yes? So we're going to move 1 unit to the left because we're adding, not subtracting. Next, you deal with the multiplication. That means it's going to vertically stretch by 2. And then the vertical shift, which is we're going to go down by 3. And that's your final result. Now let's do this one together. We're going to do everything, including the graph. Okay. First thing I want you to do, though, is help me identify how many transformations we have here. So I don't need you to tell me what they are. Just tell me how. Oops. Let's keep moving. Sheesh. Oh, there we go. So I don't need you to tell me what the transformations are yet. I just want you to tell me how many do we have here. Okay, I have 3, 4. Okay, let's count them together. I'm going to rewrite this to make it very clear for you to see how many. Okay? Now, you don't have to rewrite the function every time, but it would make it easier on you. So half is negative multiplied and negative. So looking at it like this, how many do we have? It's 4. Now, 2 of them are the same type, so you can technically say 3, but they are 4. So in a fun way, you were all right. So here's what they are. This right here is a reflection. Since it's outside, this is what? A vertical reflection. Yes? This is a vertical reflection. Now we're multiplying on the outside, so this is a vertical stretch. Oh, sorry, no, it's actually a shrink since it's a half. Yeah? This is a vertical shrink. Okay. We have a negative over here. That's another reflection. This is a horizontal reflection. And then we have an addition here, which is horizontal shift. Now here's a question I got before. Why did I rewrite it like that? Why did I turn the 3 positive and take out a negative? Well, if you notice here, if I want to rewrite the value under the root, just reorder to make the x first, it's going to be negative x minus plus 3. Yes? So that's what I did. That's it. Now, you can, if you want to, which I didn't do here, but you can flip the sign. So if I take a negative out from both, this turns into a positive x, and the 3 turns negative. If you want to do that, you can. But I thought it didn't matter since the shift is already identified. Yeah? But anyhow. So, as a result, these are the the transforms I need to do. Yes? Okay. And for the sake of being very specific, let's deal with that one to be very, very correct. So I'll make this a negative and put parentheses. Okay? So there. That's our new function after I rewrote it. Now let's graph it. I'm going to do them one by one. Now again, the order says you start with the horizontal shift, which means this one. So, okay. I'm going to graph the original function here. It's the graph of the square root of x, which we saw at the beginning of lecture. Kind of like this. Yes? Okay. Now, I'm going to shift that by -3, which means I'm moving to the right, yes, by 3 points. That means we start right here at the point of 3 for x instead of 0. And it's supposed to behave the exact same way because nothing else happened to it yet. So this is my new one. All right. Next is what? Multiplication. So the multiply by 1/2. So this is supposed to get halved, grow at a slower rate for y. So, okay. So here at 3, we didn't move it still. I'm going to make it grow slower. So it's going to be like a little below, literally a half. Yeah. Next, I'm going to deal with reflections. Now there's 2. I'm going to reflect across the y-axis and the x-axis. I'm doing both. And it doesn't matter which one you do first. So let's do across the x-axis first, since it seems easiest. So I'm going to do this one. Like that. So we flipped it across the x-axis, as you saw. Now I'm going to flip it across the y-axis. So it's going to turn like this. So I flipped it twice. Now it's across the y-axis. And with that one, we are done. This is my new function. Let me try doing it in a different pen. I wanted to do the last one in a different color, but I forgot. And black is a color you can't see anything over. Too bad. So this is your final function. Let me try graphing it here, even though it's smaller. I just want you to see the final result without all the distractions. That's what it looks like. Now, on the test, I will most definitely give you a question like this. I do not expect you to use a table and points and just try to be as specific as you can. However, you do need to follow a set form in a way, yes? So if I'm asking you to graph a root function, for example, and I give you the parent function and it looks like this, please don't give me the final result to look like a v, which is an absolute value function, for example, right? Other than that, I don't care how wonky, as long as you're right. Meaning, the shift happened correctly, that you halved the function, that you reflected correctly. That's what I care about. I don't care how exact the graph is. Because again, I don't want you to draw a table and graph each single one point by point. That will take you forever. I expect you to do it just like I did now. It doesn't have to be exactly to scale. But the points, anything concrete, like for example, the shift by 3, I need to see that happening correctly. The reflection across the x and y axis must happen correctly. Yeah. And I think your homework has a few questions like this one for you. But yeah. Does anybody have any questions? If not, we are done for the day. Oh, but I need to take a photo. Let me do that real quick. All right, you guys. I hope you enjoyed the rest of your morning, and I'll see you on Tuesday.